previous video, I tried to convince you that the fraction 1/3 was equivalent to 0.3 repeating, and we accomplished that through long division. But have you ever wondered how to get back from a repeating decimal back into a fraction? If the decimal doesn't repeat, then we can use the place value of tenths or hundredths to rewrite the decimal as a fraction and then reduce. But how do we do that when we have an infinite number of decimal places? The answer to that is dependent on an algebraic technique that I'm about to show you. So let's take this number, 0.3 repeating, and convert it into a fraction. The key to this is to assign this quantity a name in the form of a variable. So let's just call this number n. Now remember that 0.3 with a bar on top of it means 0 point and then an infinite number of threes after that. So the technique here is to multiply both sides of this equation by a power of 10 that will be sufficient to get the decimal point past the first repetition. And since this number only has one repeating decimal, I only need to move the decimal point one spot. So that means that I can multiply both sides by 10. So we're going to take this equation and multiply both sides by 10. We will get 10n equals, now remember that multiplying by 10 moves the decimal point to the right one space. So we will now have 3 point and then still an infinite number of threes to follow. But remember that the 0.3 repeating is n. That is how we defined it in the beginning of this problem. So if I wanted to remove all the threes that are repeating, I could subtract 0.333 repeating. That is also called n. So I'm going to subtract from the left side an n. Remember that a major theme in algebra is fairness. What I mean is that since two quantities are claimed to be equal, if I change the left-hand side of the equation in some way, then I have to change the right-hand side of the equation in the same way in order to maintain the equality. So when I subtracted 0.3 repeating from the right-hand side, I could have subtracted 0.3 repeating from the left-hand side, but remember that n and 0.3 repeating are equal. So what I've done is I've subtracted the same amount from both sides. So if I simplify what I have here, 10n minus 1n is 9n. And when I perform the subtraction on the right side, notice how the threes that are repeating afterwards forever cancel out, and it leaves you with just a 3. Not roughly 3, but exactly 3. So notice how with this move, we have eliminated all the repeating decimals in our problem. Now our goal was to find a way to write 0.3 repeating in a different way. And we called 0.3 repeating n. So in this equation, if I now solve for n by dividing both sides by 9, I have isolated n. 3 over 9 is 1/3, and n was 0.3 repeating. So 0.3 repeating is 1/3. Let's try another one. What if I have a number where 2 of the decimal places are repeating over and over? This number is 0.52, then another 52, and it keeps going with the 5 and the 2. Using the technique we learned in the last example, we want to multiply both sides by something that's going to get the decimal point past the first repetition. So I need to get this decimal point over here, past the 2. You may have guessed it, that we should multiply both sides of this equation by 100. So I'll multiply the left by 100 and the right by 100. This gets us 100n equals, so we'll get 52 point. Now remember, after that decimal point, there are more 5s and 2s. So it'll continue to be 5, 2, 5, 2. That will continue forever. As before, this decimal point and repeating part are equivalent to the original amount that we started with, n. So we'll subtract 0.5252 repeating from the right side, and on the left side we'll subtract one of the n's. Now we have left 100n minus 1n is 99n, and this repeating decimal will cancel out, leaving you with just 52. Now that we have eliminated the repeating decimals, we can finish solving for n. So we'll divide both sides by 99, and we get n equals 52 over 99. We should try to reduce this answer if possible, but this one is in simplest form. Now you might notice something curious. Suppose my number was 0.52 without repetition, then as a fraction, this is 52 over 100. But when I do have the repetition, 0.52, where the 5 and 2 are both repeating, we get 52, but not over 100, over 99. That might suggest a trick that we can use to convert repeating decimals into fractions very quickly. Let's try another one with 3 decimal places repeating. In order to get the decimal point past the first repetition, we need to move the decimal point to the right 3 times, which means that we should multiply both sides by 1,000. We'll multiply the left by 1,000 and the right also by 1,000. We'll get 1,000n equals, and then moving the decimal point over 3 times will get us 961, but I still have 0.961 repeating afterwards. Using the technique we learned before, we're going to subtract 0.961 repeating from the right side, but that is called n, so we're going to subtract 1n from the left side, leaving us with 999n equals, that repetition will cancel and we'll get 961. Now solving for n, we'll divide by 999 and we'll get n is 961 divided by 999. Notice again how this is suggesting a quick trick for converting a repeating decimal into a fraction. If the decimal has 3 repeating values, you just write those 3 repeating values and divide by that many 9s. So not 9 multiplied by 9 and another 9, but a 3-digit number that contains all 9s. This is a quick way to get there. Now, sometimes you'll get a fraction that actually reduces, so make sure to remember to finish reducing. However, this trick does not always work. If all of the digits are repeating, then you can put those digits over a series of 9s in the denominator. However, in this example here, I'm still using 9, 6, and 1, but notice how the bar is only over the 6 and the 1. It is not over the 9, so the 9 is not repeating. So we have to do something a little bit sneaky here. What we're going to do is we're going to multiply both sides by 2 different things. Once we're going to multiply by something to get the decimal point before the repetition starts, so here, and then separately multiply by something that's going to get the decimal point past the repetition. So here, multiplying both sides by 1000, we'll get 1000n equals 961. But remember that after that decimal point, there's more sixes and ones. So 6, 1, 6, 1, 6, 1, forever. Don't forget, the 9 does not repeat. Now, to get the decimal point to be in the blue spot, just past the 9, but before the repetition begins, we only have to multiply by 10. So we're not multiplying this pink line by anything. We're going back to the original and multiplying both sides by 10. So we'll get 10n equals, getting this decimal point to move over just once gets us 9.61, and then more 61, 61, 61. What we accomplished here was getting two numbers that both have a 0.61 repeating. So if I subtract these two lines carefully, I have 990n. Notice how that's different from the previous examples we've done. 990n. But here, these decimals are going to cancel out. I have to carefully subtract 9 from 961, which is 952. Then dividing both sides by 990, we get n equals 952 over 990. Notice how that does not have the same pattern as the trick that we showed before. The trick that we showed before does not work this time because not all of the decimals are repeating. You can only use that shortcut if all of the decimals are repeating. Also, notice how the numerator and denominator have a common factor of 2. So we can reduce this to be 476 over 495. If you type this fraction into a calculator, you will see that the decimal equivalent is 0.961611616. Recall that in the previous video, I asked you to challenge your intuition and see if 0.9 repeating was close to 1 or was it exactly 1. In order to answer this question more firmly than we did last time, maybe we can take the quantity 0.9 repeating and call it n and use the technique we just learned. Since there is only one decimal place that repeats, multiplying both sides by 10 will be sufficient. So we'll get 10n equals 9 point, and then more 9s after the decimal point, 9 repeating. I'll subtract n from the left, but I'll subtract 0.9 repeating from the right side. Remember that n and 0.9 repeating are equivalent. And I'll get 9n equals, we get just 9. So 9n equals 9, which suggests that n equals 1. Not close to 1, but exactly 1. Therefore, 0.9 repeating is exactly 1. I hope you enjoyed this video. See you next time!